welcome to the session on search problems and CSPs. So this covers week 9 and week 10 worth of content and does not go into games and adversarial search yet. That's for next session. So let's get started. Basic stuff. So a search problem is basically where you have a goal and you try and find a sequence of actions that lead you from your initial state to your goal state. And when you have a search problem, you need to define a couple things. And this is universal to all search problems. So you obviously have to have a state space. These are like the nodes, right? And the arcs between them represent transitions, how e.g. actions like to get from one state to another. Here you have your initial state, which is where you start. You have your action set, which describes the actions that can be executed by any given state. The transition model is a mapping between the states and the actions. So like what results when you perform an action on a state, what's the result? You obviously have to have a goal test to know if you've reached your target or not. And finally, you've got to have a cost function that evaluates your kind of path or the actions you're going to take and tells you how good it is or how effective your solution is. And that's universal for all search problems, and that's essentially how we define one. So search problems go well into search trees. And what is a search tree? It's just the process of solving the search problem in a nice visual way. It can be abstracted into a tree form, where your initial state is the root and the children are the corresponding successors. So it's what you visit next. And the nodes show the states and corresponding to the plans the path that you're generating to reach a solution. So just generic tree search. This is stuff we did in AI1, but just to remind you, the frontier is a store of all these nodes that we can see exist, but they're waiting to be expanded. Essentially, we've expanded one that's adjacent to it, but these are the ones that we can expand next. That's the frontier. What do I mean by expand? It means to find and display the children of a node, or a specific child if I want to expand a specific child. And the expansion strategy, meaning the order in which we expand nodes in the frontier, depends on what strategy we choose, like depth first search, breadth first search, and so on. This is a general pseudocode for, a generic search tree. Not very useful, but it kind of describes how it works, like expanding the frontier. In terms of breadth first search and depth first search, we did do it in DSA and uninformed search in AI1. So I'm not sure how much you want me to go into detail here, but I have linked it to my notes on the stuff from last year. So just really, really briefly, in breadth first search, you kind of go in layers. So you start at the top and then you expand each row as you go down, aka you go like widthwise, not downwards all the way to the bottom. And so this means you expand all the children of a node, and then proceed to go to the next node in the layer down. This is not the best for search problems because, well, in a search problem, you need to reach a solution, which means assignment of all the variables, or most of them at least, and that will only occur on the bottom layer. So going through in a depth first search means you expand every single possible node before you reach the layer where you actually start getting solutions. What's more efficient for search problems is depth first search. This is where you go down the layers. You don't expand the entire width. You pick one of the children and then you pick that child's child, and then so on. You keep going down until you reach an assignment of all the variables and then decide if it's a solution or not. This is generally more efficient since you actually look at potential solutions rather than computing partial solutions all the way until the end, until you start reaching real solutions. But at this point, you've explored like most of the entire tree, which can be pretty inefficient. So in search problems, we prefer to use depth first search. We'll go back to the original notes. So here, we can now look at constraint satisfaction problems. So until now, I'm just checking if there's any questions. Nope. Okay, cool. So yeah, until now, basically, we've been looking at a kind of problem known as planning. So planning is when you need to plan a set of actions to reach a specific goal. They're not all the type of problems that you can have. For example, what we'll look at now is constraint satisfaction, which is an identification type problem. So here, there is no like preference. There's just constraints that need to be satisfied. If the constraints are satisfied, you're good. That's a solution. Whereas with planning, you often try and go for like, oh, what's the most optimum solution, and so on. And then you have a set of actions that leads you to a solution that need to be conducted in a specific order to get from the initial state to the goal state. This is not the case with identification. Identification needs you to assign variables. So there's no order, there's just an assignment of variables that satisfies the constraints of the satisfaction problem. That's why it's called constraint satisfaction. So that's the subtle difference between the two. And yeah, here's the difference between planning and identification. So just like how we did with search problems, we looked at the components, initial state, goals, goal check, all of that. We're going to look at how to formulate a CSP and all the parts of a constraint satisfaction problem. So in order to formulate one, you just need three things. You need the set of variables, you need the domain for each variable, and you need a set of constraints. Now, a fourth thing that will help you solve it is a constraint satisfaction graph where you visually represent the problem, but that's not explicitly required to formulate a CSP. So, moving forwards, we can see some more differences between the CSP and planning, which is what we were looking at before with search trees and stuff. But yeah, we won't go too much into depth in that anymore. So constraint graphs, essentially, I mentioned this earlier, as like something that would help you solve the problem, but it's not explicitly required to define the problem. All it does is it represents the relations among the constraints in the CSP, where nodes correspond to the variables and arcs reflect the constraints. So it doesn't give you any new information that the variables, domains, and constraints didn't already give you. It just visually represents it. So let's look at two examples just off the bat of the information that I've given you right now. So here are two examples. There are two houses, house 1, house 2. Each house has a different color, which can either be blue or red, and a different pet, which can either be cat, dog, or fish. We also have the following constraints. House 1 does not have a dog nor a fish. The blue house has the fish. So the question is, which color and pet each house has? So that's the problem, right? And we've been given the constraints. So let's now formulate a CSP. First thing, as I said, we've got to think of is the variables. Here, we can say the variables we're dealing with is color and pet. Specifically, we can relate each one to a house. So we can have color 1 and color 2 representing the color of house 1 and house 2 respectively. Or we can have pet 1 and pet 2 representing the respective pets of each house as well. So I'm going to go ahead and say these are the variables we're working with. I don't think there are any more. Following that, we can then define the domains of these variables. So let's go through each variable and define their domains. So the color 1, domain being the range of, the domain is essentially, in case I didn't make this clear before, all the different values you can pick from to assign a variable. So the different values that color 1 could take, for example, is blue and red. So that's the domain of color 1. Same with color 2, the domain is blue or red. With pet 1 and pet 2, like the colors, have the same domains, each one just being cat, dog, or fish. And now we have to set the constraints. So these are the rules that must be in place in order for the problem to actually, work out in real life. So one you can say straight off the bat is that we've been told here that there are different colors and different pets. So pet 1 is not equal to pet 2. Similarly, color 1 is not equal to color 2. Next, we can also say that it says here house 1 does not have a dog nor fish. So you can write that out as a constraint. We have a question in the chat. Let me just quickly take a look. Aren't the domains also kind of constraints technically? Well, not really, because the domains will tell you what values will exist or can be taken by the variable in question. I can see why it might seem like a constraint, because you're thinking like, oh right, so this gives me a set finite number of values that the variable can take, therefore it must be constraints because it's constraining the values of the variable. You're right that it does do that, but we don't explicitly call that a constraint because the domain considers all the values that a variable can take. It doesn't actually constrain it at all. It literally just defines that this is what is like. It's not even what's possible because the constraints actually define that. For example, the domains would tell you like, color 1 can be pet 1, let's say, can be dog, right? The constraint for the domain for pet 1 would contain cat and dog, but we know from the constraints that it's dog can't be there and fish can't be there. So in that sense, it's not actually possible to have every value of a variable's domain be assigned to it. It's just all the values that we can explore, essentially. Doesn't mean that all of the values in the domain are possible, which is why it's not a constraint. A constraint defines what values are possible. I hope that makes sense. Which color? We've defined the constraints and stuff here. So as you can see, as we discovered, they've got the ones here that says color 1 and color 2 is not equal to each other. Pet 1 is not dog or fish from that one there, and the blue house has a fish, hence why they've put these two if statements in. If color 1 is blue, then pet 1 is a fish, and they've done it for both the colors. So this is how we'd formulate a simple CSP. And over here we have a graph. So on the graph, essentially, we want to just list all the variables, and we often write down constraints and point the constraints to whichever variables they apply to. Cool. We'll just briefly look at the Sudoku one. I've got another question in chat. Domain, I think you got it. And they said we have to write these mathematical notations strictly, so we just sentence won't get us the marks. Yeah. So to write it mathematically, we'll look at that. We'll look at that in later on. So here's another one, Sudoku, right? We can see that each open cell has variables and domain, and the constraints here are written out in English, as we know the constraints of like Sudoku. Moving on then. So if you want to relate more than two variables, you use a square to represent the constraint. In a graph, I'm saying. You use a square to represent the constraint and connect all the variables involved to that constraint. So for example, here, this would be the Sudoku graph. So you can see that it's just pointed to all of the boxes that it applies to, and it just says all different. Now, yeah, you are right, it won't just say all different, you'd have to put some mathematical notation in, but that's how you show what constraints would tie into what variables. And finally, there's just a little note here on like what different kinds of CSPs you can get. Finite domain, infinite domain. You can get a different amount of constraints as well. And just a quick note for complexity. If a CSP has n variables and the size of each domain is d, then there are O of d to the n complete assignments. So it's exponential complexity essentially as the variables increase. So it's not in P. constraint solving. So that's why we're going to look at different tricks and techniques to make it more efficient in the next part of this. So let's move on to the next part. Here, right, we're going to look at different ways to solve a formulated CSP. So in constraint satisfaction problems, states are defined by the values assigned so far, and this is what we call partial assignment. If we've assigned some values to try and get to a solution without having assigned all of them just yet. So the initial state is just empty, so nothing's been assigned yet. And the successor function essentially assigns a value to the unassigned variable. And we'll look at how we choose which is the one we expand, right? It's done through a process called ordering. We'll look at that in a sec. The goal is the current assignment, the assignment essentially to reach an assignment that satisfies all the constraints. So it's done through a process called generate and test. So the exhaustive generate and test algorithm essentially generates all the complete assignments and then tests them. However, this is not efficient as we looked at in the previous one, so we need to make this more efficient, and we're going to look at how we can potentially do that. Here's a good example of one that we can look at later. Actually, I'll come back to that. So attempting to solve by breadth first search, we already looked at why this isn't the best idea. And you can see that when we do this, we have to expand all of the initial values. And then once we're done with that, then we can only move on to the next layer and so on. And since the solution is always in the bottom layer, a BSF would have to traverse all nodes, aka all the partial assignments, before finding the solution, which is not feasible in like real and like feasible graphs. Solving CSPs via DFS, right? So this is what we actually do, right? Through a various of techniques, which we'll look at now, called backtracking, filtering, or via forward checking, and ordering. So this is a feasible solution and is only reasonable when you check the constraints as you go down and stop traversing any path that is not followed by a constraint at any point. So that's what depth first search is. We know this from DSA and AI1. So backtracking, what backtracking is it essentially we assign values to variables one by one, and if we hit a dead end, so there are no legal choices that are left from where we are, we backtrack to where we backtrack by one to where we had more options, and then we try something else. And the way we improve backtracking is by filtering and ordering. Filtering, the idea is just detecting an inevitable failure before we reach that failure, so it saves us some computation. And then ordering is essentially picking the order in which we expand different children. So let's look at filtering via forward checking first. So forward checking assigns a value to one of the variables and then cross off. Then what we want to do is cross off the neighboring variables that violate a constraint when added to the existing assignment. So in this case, right, the example in this example, there are three variables, right, all with the domain 0, 1, and 2, and the constraint is b is greater than a, which is greater than c. So initially, right, all of them have the same domain, and we can see this as the initial, all of the initial states, right? All of them have the same domain. What filtering or via forward checking will do, it'll assign one of the variables. So here they've assigned a, and then they'll constrain the neighboring variable assignments to check if this assigning a to 0 will actually yield any solutions. So what they've got from here is when they've assigned a to 0, that means b, the domain of b is constrained, because the constraint was that b is greater than a. So the only values that are greater than a in the domain is 1 and 2. So b can no longer be 0, so we've eliminated that from its domain. The other constraint was that c is less than a. Now, there is no value of c in the domain that's less than 0. Hence, the potential solutions for C in this case are are, zi- are 0, as in like it's not even 0. Like there's nothing essentially. There's no solutions, which means that this assignment of A can be ruled out. It can, before we then even go and explore B and then try and go and explore C, we can just cross off this path and say that, you know, there's not going to yield us any solutions. Therefore, A can't be 0, and we're going to go check out the next value of A, which might be 1, and then they'll do the same thing. So have you got any questions on forward checking, or does that all make sense? Okay. If a constraint only involves one variable, you can instead represent it by changing the domain of that variable. However, if a constraint uses 2 variables or more, you can't do that. If A is not equal to B, you can't represent that by changing the domains of A and B. The question, oh wait, that's not a question, that's you answering his. Okay, right. Okay. So in forward checking, you're essentially pruning domains as you go. Yeah, essentially you're pruning the domains. You're pruning branches that won't work out as you go along. But we don't explicitly call it that, I don't think. I don't know. So then, now, let's move on to ordering. So in ordering, right, it's the other way we make DFS more efficient. We assign values to the variable with the fewest remaining legal values, so the smallest domain. And we do that first. That's how we choose what we're assigning. And why do we do that? Well, it's because it's more likely to fail. Counterintuitive seems like it, but it actually saves us a lot of computation if we remove paths that are more likely to fail earlier on, right? Because that saves us a lot of computing and leaves us to focus more on paths that are more likely to work later on, and that will require more of the computing power. So that can be done without having to compute essentially the ones that weren't as likely to work. So essentially, this is also called most constrained variable and the fail fast strategy. And yeah, it's essentially self-explanatory. If you have a variable with a domain that only has one possible assignment, you'd go with that. Or whichever one has the least possible or the smallest domain, you'd pick that first, assign something to it, and then get that variable sorted out before you move on to trying to assign any other variables, because it leads to the least options and the least computation later on if you think about it. Because say, I don't know, A can only be one value. Now, say you instead picked C, which can be 3 different values. Then for each value of C, you're going to have a different value of A and B sets. You're going to have to expand all of these values of C, right? Whereas if you just picked A, which said, let's say, only had one domain, only one thing you could assign it to, then you're only going to have one value of A and then go from there. So, finally, let's look at CSPs by solving CSPs by local search. In this case, what we have to do is, oh, do we have a question in the chat? Let's take a look. Wouldn't you use backtracking in a continuous domain anyways? How does forward checking work when the domain is very large, e.g. all integers? The sooner a path fails, the better basically. Paths with less options in the domain fail sooner. Any time spent on failing path is wasted. Yeah. So in an infinite domain, right, then essentially you can't really use ordering unless you have something like, you know, countably infinite and uncountably infinite, in which case you'd pick the countably infinite one. But what you'd want to do is you'd essentially have to start with something, and then that would hopefully lead you to be able to constrain other things away from all integers, and that's how it would work in an infinite domain. Why wouldn't you use backtracking in a continuous domain anyways? Why not? I think there's a conversation I think the question has been answered, but if it hasn't, let me know. Um, okay, so by local search, essentially last part. Oh wait, there's optimization after this, but yeah, local search. We looked at this in AI1 as well. Aims to find solutions quickly. Might not be the best solution. Well, there is no best solution. You just got to satisfy the constraints. But it may not be the optimal solution in case you have an objective function as well. So essentially what you do is you start with a completely random arbitrary assignment of values, literally like, pick a equals 20, b equals 36, blah, blah, blah. Just literally any random values, right? And then if the constraints are violated, you try and improve the assignment, and you just do this iteratively. The difference here is that you're starting with a random assignment. You're starting somewhere random in the tree. You're not starting from an empty assignment. This is useful for like when Hux was saying like an infinite search space, or like when you have all integers. So in a reasonable time, you'd be able to use a local search instead of trying to use systematic search, which would fail because you would try and consider the entire space. The steps are essentially, as I explained, you randomly generate an assignment, and when the constraints are met, you just iteratively perform these two steps, which is explore all the neighbors of the current assignment and choose the neighbor that violates the fewest constraints. If all the neighbors violate the same number of constraints, you just choose randomly. Then finally, let's look at optimization. This is a search problem where with preferences called the objective function, right? It's where local search makes more sense. So, it's where local search is a drawback because it doesn't find the optimal solution. It just finds a solution because it's trying to do it in a reasonable time. So you can either have single objective optimization where you just have one thing you're trying to maximize or minimize, or you can have multiple as well, like, distance and time when you're looking at maps. Tree search off methods may not work for optimization problems because local search methods are more effective, and tree search, if the domain is too big, it's not as likely to yield you good results. So the traits of local search are, as I've said now a couple of times, it's faster, can deal with problems in a search state that's difficult to represent or formulate, especially if the domain is very, very big or infinite even. And here are some ones that we looked at last year as well: hill climbing, simulated annealing, and population-based local search. We're not going to be expected to carry these out. We probably won't be expected to remember them either, because looking at the revision slides that we were given during the revision lecture, local search did not come up on that. And it wasn't mentioned, not even, like, let alone the types of local search. Like, local search just wasn't mentioned at all. So I doubt we'd get a question on local search. I did say we were going to go back to one of these examples here. So in this case, we want to formulate the CSP following a crypt arithmetic puzzle. So here, let me just try and make this a little bit bigger. So here we have essentially TWO plus TWO equals FOUR. 2 plus 2 is 4. And we want to find values for the variables T, W, O, F, U, and R. So what we can do first is this kind of going to combine all the skills that we've learned so far. We're going to formulate the CSP. It doesn't ask us to solve it, it just asks us to formulate it. So I'm going to switch screens to the whiteboard and do the same on OBS. Right, can you see the whiteboard? It's just an empty whiteboard right now. But OBS as well, let's switch to scene 2. Okay, cool. Can everyone see the whiteboard okay, yeah? Cool, alright. Then let's get started. Whiteboard, we go. So I'll paste in the actual question as well. It might help with the problem. So this was the question. And let's now look at the solution. So firstly, right, chat, what do we need to define first when we are trying to formulate a constraint satisfaction problem? I'm going to leave this one up to you guys. So what's the first step? What's the first thing we need to define? The variables. Yes, let's go, Hugs. Right. So, oh, that's very, very, okay, right. Hang on, let me zoom in a little bit. Okay, right. So, let's define the variables. So, yes, let's go, Ash, MetaMask. Anyway, so what are the variables here? So, can anyone guess what the variables are? Hang on, is it showing the right screen? Oh, hang on a sec. Oh, okay, one sec. I'm actually sharing the wrong screen. 1 minute. Okay, right. That's why you guys are okay. That's why you guys are okay. Talk about MetaMask. That was so close. I accidentally then almost leaked my MetaMask secret wallet. Okay, my bad, guys. My bad. I did not. It didn't actually show the MetaMask wallet secrets, did it? Okay, that's good. Right. So here we have the what I was actually supposed to be showing, and that also means that OBS has been recording the wrong thing. 1 sec. Let me pause the recording. Okay, right. So this is the correct screen for those watching on YouTube. Right. Let's get started. So essentially, right, what is going on in the chat? Okay, I'm not going to question what's going on in the chat, but as Jess put, the variables are TWOFUR. So TWO and F. We're not including the O in 4 since we've already obviously included it for 2. Come. Okay, so next, as Hux did say, we need to define the domain of each of these variables. So if we do that, we can get...
Ash said hello, guys.
Hi, Ash. I don't know how you do that, but okay. So essentially, all our variables will have a similar domain. So TWOFUR will be... Now, this is what you'd say with the mathematical notation. You'd write this sign, and then you'd put a set, and you'd write it in set notation, so all the numbers from 0 to 9. So that is our domain for these variables. People can't hear me?
Guys, try rejoining the stage if you can't hear, because I think it's coming through.
There's a lot of people saying that they can hear me as well.
Yeah, okay. Okay, cool.
What is going on in the chat though? Why is there GTA gameplay video? This doesn't look like GTA actually. Is that Cyberpunk? Anyway, never mind. Right. So basically, right, there's more variables that I just realized that we need to consider as well. So it's not just the ones that the ones that Jess put in the chat. There are a few more. Can anyone guess what they are? When we do column addition, we also have to factor in other things, the carryovers or the remainders. Exactly. So yeah. The remain. I mean, I'd call them carryovers, I guess, but yeah. Um, Essentially, we can call this like C1, C2, because essentially the carryover from the units column will be C1, carryover from the tens column will be C2, carryover from the hundreds will be C3. And let's go with that. Is that clear to everyone? Cool. So the domain, we'll also need to now have domains for these carryovers, which actually would just be the same as... Actually, no, hang on a sec. The carryover domain would be actually less because you can't have every single number in a carryover with just the units. I don't think so. Actually, would it be? I think you'd have all the. Right. Yeah. So C1, C2, and C3, right? They can only be 0 or 1 because the highest value that we can add is 9 plus 9, and that gives us 18, 1, 8. So the highest value of a carryover can actually just be 1, and the lowest value will be 0. So there's something to note here that the domain of the carryovers are actually constrained. Does that all make sense? I hope it does. Right, so as Huck said, we needed to get the variables and the domains. What's the next step? To formulate a CSP. Constraints. There we go. Huck's again. Okay, right. So, wait. Yeah, you can have all. Yup. Yeah. What is the we can have all? We can't. Are you talking about the carryovers, Shay, or Vivan? What do you mean, like, yeah, you can have all? Oh yeah. No, I thought Shay, Ash, and Kevin said yep to that. Yeah, it was carryovers, but I realized it was wrong. Lol. Okay, right. Anyway, cool. Let's continue then. So constraints. The constraints. Okay, right. So for the constraints, now it gets a little bit tricky. So let's get started with the constraints. We are going to write the constraints in mathematical notation. We're not going to just use words, and that's what's going to be different here to what we did before. So let's just quickly look at the problem again. So each letter represents a unique digit, so that's one constraint already. They can't be the same, so no two letters can be the same. The goal is to find the digits that such equation is verified. Okay, so we'll look at that in a sec. So let's write the first constraint that we already know, which is what we call is, we can go through and write down all the permutations, like, you know, t is not equal to w and t is not equal to o and all that. Or like what we can do, and what they did in the answers, is just put a function here called allDiff, and this essentially gets the message across. Otherwise you'd have to have an insane number of permutations of like everything saying this is not equal to that, this is not equal to that, and so on. So these are just all diff. That's our constraint number 1. Right. So this constraint by itself won't help us formulate the problem. We, in fact, let me bring this down so we can see it. Okay, so we also need to consider other constraints. So the other constraints we can easily see here is that O plus O equals R, and the carryover you have to consider. So how we'd write that as a constraint is O plus O equals R plus 10 times C1. Because it's a carryover, it's actually 10 times that amount. So, for example, if we had 6 plus 6, right, the answer would be 12. So it's not just... So R in this case would be 2, but it won't be 2 plus 1, it'll be 2 plus 10. Hence, the carryover being 1, you'd have to multiply that by 10, and then add it to the units column, and that's how you'd get the value. So this is our first constraint. Now, looking at that, can anyone give us the constraint for the tens column? Okay, Shay has given us all of them here, I think. Shay, man, you have to let other people answer too. Okay, right. W plus W equals U plus 10 C2. And another constraint would then be T plus T is equal to O plus 10 C3. And finally, constraint 5 is F is equal to C3, because that's the final constraint. Right, someone has requested to speak. Okay, let's check out what Aaron's saying. Aaron, are you coming onto the stage? I don't know. Aaron has revoked his request to speak. Okay, I guess he doesn't want to speak anymore. It's okay, you don't have to speak. Cool. So these are our constraints. Let me just think, do we have any more constraints? I mean, what you can say is that, and what they've got as well, this is often like a forgotten one, you got to look at the zeros, the zero constraint. So what values can't be zero? And we know that the value of t can't be 0, and the value of f can't be 0, since the leading value is not going to be 0, essentially. Otherwise we wouldn't have the t or the f there. So these are our constraints. Cool. Now that's actually the question answered, right? That is, we've formulated the CSP because we've got the variables, the domain, and the constraints. I just want to take it a step further just to show you how everything works and formulate the graph as well, right? And the graph of the CSP. So what's important to know when we look at the graph is that we can see all of the constraints. So here, essentially, how do we do the graph? So the graph, we first start very easy by just listing out the different variables that we have. So what I'll do is I will just list them out. So let's do the one from the 4, so the f and the so yeah, so we have different variables, f, t, u, w, r, o, and we also have the carryovers as well, so c1, c2, and c3. Let's move this down a little bit. Oh man, what? Can we not? Okay, anyways, never mind. Let us, oh, okay, it's working now. Right, so now we've listed out all the variables, we have to look at the constraints. So the first constraint, we looked at this earlier, just you got to put in the constraints and you got to tie it in with which variables they relate to. So the first one, all diff needs to relate to all of these values. It's got nothing to do with the constraint, the carryovers. So what we can do here is we can write out that constraint, all diff t W, O, F, U, R, and let's draw circles around these to show their nodes. And essentially this is in a box because it's a constraint. And we link it to all of these. So now we know that these are held by this constraint here. Then we now look at the other constraints we had. So essentially we have got to have boxes that say O plus O equals R plus 10C1. Right, what does this link to? Well, we can see that this links to O, it links to R, and it also links to C1. Don't know why I drew C1 on that side, but okay. You know what? This is gonna get really complicated if I have these this way around. So what I'm gonna do is I'm gonna actually just relabel the C's. So the C3 is over here, and this is C1, this is C2, and that's C3. Okay, so this relates to C1. Okay, let me draw circles around these as well. So what you'll notice here is that all the variables are inside circles, they're the nodes, and the constraints are inside boxes. Have you got any questions in the chat? Okay, I don't think so. I mean, I think all the question. These constraints are wrong. Why are your constraints wrong, Shay? Wait, what? The ones you put in the chat are wrong? What's wrong with the constraints?
You have to add the carry of the, like for the 2 plus 2 is 4. You have to do O plus O plus, no, O plus O is, so that one's fine, but then when you do the W plus W, you also have the C1 at the top of your adding on the left side of the equals like this.
Oh yeah, okay, yeah, I see, yeah, you're right. You have to look at the C1 as well. Yeah. Okay. Yeah, I see what you mean. Good catch. Okay. So this one's fine, and from all of these ones you'd actually have to have another one. So this would need to be like plus the carryover, so it'd be C1 plus W plus. So is this what you mean? Yes, okay, good catch. And then F is equal to C3, so I think that stays the same. So does this actually change the domain of the carryovers? So the largest value you can have is 1 because 18. Now that means the largest carryover is 1. So that means that you can have maximum 19. Yeah, no, I think it's fine. 8 plus, it'd be 9 plus 9 plus 1, which is 19. So the largest value of the constraint, sorry, the carryover is still 1. Okay, that's good. Okay, so yeah, we can continue. Okay, luckily we hadn't drawn anything wrong here just yet. The next constraint that we have, you know, I'm just gonna like put these constraints in from here because I'm gonna write all of them out again. But essentially, like, I'm not going to go through the entire one because it'll take absolutely forever, but essentially what we do is we can, like, copy this. Why won't it? Let's copy this, right. Okay. What is, okay, right, the whiteboard is lagging out, but essentially you'd have these constraints and you'd link them to, like, all of the values here. And if I switch back to the other screen, you can see what the final graph would look like. And yeah, obviously, yes, we need to ensure we have the correct constraints. If we switch back to the Notion, we can see that this is what the answer would look like. Let me switch this back as well. Okay, right. So essentially, as you can see, they've got the same thing as us here, and yeah, they've actually remembered the carryovers as well, which I forgot. Thanks for reminding me, Shay. And yeah, they've essentially got all of these constraints here linked up to the ones that they affect. If they're involved in the constraint, you draw a connection from the box to the corresponding node for the variable. And yeah, that's how it works. And there you go. That's how to formulate a CSP, and then also how to draw a graph. And we've also just looked at how to use a graph with DFS, including filtering and ordering, to solve the CSP. So yeah, thank you guys for watching. That will be everything on search problems and CSPs. Thank you. Right. Gotta love Microsoft Whiteboard. Yep. Okay. If there's no further questions, I will end the session here, or end the recording now. Thank you guys for joining, and I'll catch you tomorrow for the final Texiland AI session on adversarial search or games.